is Ronald Portoreal, this is Matthew Cozo, and Sean DePascal. We are the Mech Panthers, and our project is the NASA Lunar Robotics Project. The purpose of our project is to design and build a mining robot that can traverse the lunar surface. We have a weight limit of 80 kilograms, which transfers to 176 pounds. We also have a 50 kilobyte per second transmission data limit. We plan to implement a hybrid design where we have a fully autonomous and manual control. The electrical computer team is handling the autonomy part, the fully autonomous part, and they will be using the CME Cam 4 for the tracking. Additionally, we have a dust-tolerant design where we need to seal up the components. The terrain on which we will be traveling on is the BP1 regolith. It has a density of 50 to 100 pounds foot cubed. And the first 2 centimeters are fluffed to the 50 pound foot cube consistent density. We also will be encountering 1 foot wide by 1 foot deep craters, and there will be naturally occurring rocks scattered throughout.
For our design considerations that we initially took into account, we looked into the mobility system, whether we wanted to use wheels, treads, legs, or some sort of hybrid of them. We also looked at the motors we wanted to use, as well as gearboxes if it would be necessary to speed up or slow down the motors. The collection mechanism, whether we wanted to go with a scoop or a continuously operating conveyor belt system, as well as for the dumping mechanism, how we would deposit the collected regolith into the hopper that's on the side of the field. And finally, for the control system, what sensors and cameras we would use for the navigation of the terrain, and how they would adhere to our data transmission limits.
For the mobility system, we looked at a couple of options. The first for the wheels, they would be the cheapest and easiest to implement, but they'll give us the least amount of traction. So we considered a hybrid system that would increase the traction, but it would also increase the weight and the cost. Ultimately, we decided to go with a track system that would give us the most traction, even though it would be the costliest and allow some dust into the system.
For the collection, we had 2 options. We had a conveyor system or a scoop mechanism. For the conveyor system, we had the advantage of a continuous pickup, while the disadvantage was a higher cost and higher complexity. For the scoop mechanism, it was easy to implement and low cost, but it required more power and it had limited excavation.
Design changes that we made to the frame from our initial concepts as we progressed along. We shortened the overall frame length. This was done by placing the collection mechanism outside of our footprint. The purpose of this was so that we could find treads that would adequately suit the length of our rover. We were having some trouble before we did that. We also switched to a thicker frame material. This unfortunately added weight, but it allowed us to get the material faster and much more cheap. And also we added a support frame for our collection mechanism as well as the dumper bin in the rear. The final design of the frame, it's all 6061 T6 extruded aluminum box tubing, 2x1 for the frame and 1x1 for all of the collection mechanism. It's welded in all of the major joints as well as riveted in all of the minor joints. We have roughly 6 inches of ground clearance between the treads that will allow us to traverse the terrain without any issue. The center of the rover itself is compartmentalized for the electronics so that they can be organized as well as free of the dust particulates. And we also integrated the dumper guide rails into the supports of the frame. Those are those angled pieces that you see.
The construction of our frame was done in 2 parts. First, the bottom base. We ran a SolidWorks simulation using the Von Mises stress criterion and applied a load of 1,200 newtons, which is about 250 pounds across the top of the base. We got a factor of safety of 9.9. Once we finished the top section, we reran the simulation, this time putting a load of 1,700 newtons, distributed based on where the regolith will be held, and as well as the weight of the collection mechanism. And we used the same criterion, and we got a safety factor of 14.
For the drive system, we implemented the Super Droid treads. They are sprocket driven. The purpose for the sprocket is so the belt doesn't slip off. Additionally, they have UHMW shoulders. This material is made out of durable plastic, and it has a consistency of Teflon and the coefficient of friction. Additionally, this Trax has a profile rubber tread. Originally, we wanted to buy the sprockets from the company, but due to cost limitations, we designed the sprockets ourselves. The original design had idlers here in the front, and as the belt got worn down, we had to add tensioners to it. So we changed that part of the design. Lastly, this hub here is aluminum, and it transfers the power from the shaft to the sprocket.
For our design changes for our gearbox, our initial orientation was horizontal. We switched it to a vertical design simply for easy mounting onto the frame itself. We had a sprocket-driven output shaft initially, where we would have an output shaft. The output shaft of the gearbox would have a sprocket on the end, driving its chain to the drive sprocket. This presented more points of failure as well as more areas for dust to settle in, so we switched that to a direct-driven output shaft. So the output shaft of the gearbox goes directly into the drive sprockets now. And finally, we switched from an open design, as you can see on the top right, to a partially sealed design in the middle, to a fully sealed design on the bottom right. This is a cross-section view, so you can see the internals.
In order to find the reduction that we needed from the gearbox, we had to run some calculations. The first was how much torque we would need to move the rover. We took this off the internet, off of University of Florida. They provided us with the formulas for the resistive force that would be experienced because of the weight of the rover. Our surface of where we'd be traversing, we selected sand dune, which is the worst possible surface to out of this calculations. We implemented a slope of 15 degrees, and once you add all the forces acting against it, we can find the torque needed by each wheel. After that, we input the motor torque, and then that gives us the reduction we needed of 15. Once we found that reduction, we then had to find the minimum number of teeth needed by the pinion gear. So using the formulas from Shigley's mechanical design textbook, we found that along with the transmitted loads on the gears. On the website where we purchased the gears, they had stainless steel and aluminum gears. We ran the analysis at normal load and max load of the motor to find the safety factor for each gear. All of them were above 1 with the exception of the aluminum at max load. That was below 1. However, we ran it using a life cycle of 10 to the 4th instead of 10 to the 7th because we figured it wasn't going to be going on that long. That did bring it up above 1. Either way, in the end, we ended up going with stainless steel for the added safety, as well as the fact that the cost difference wasn't much between both.
The final design of the gearbox, it is a 15-to-1 speed reducer that operates in 2 stages, each stage with a 16-tooth pinion going to either a 60 or 64-tooth gear. The frame of the gearbox itself is machined out of 6063 2x4 aluminum box tube. Into the frame itself, we have the press fit bearings where our shafts ride. The shafts are all case hardened steel. And we have covers 3D printed for the gearbox plates to ensure that no dust would enter and foul with the gears.
A couple of design changes made to the dumping bin and collector. First, for the dumping bin, we made it change it from a static to a mobile bin. Using a system of pulleys, we lift and lower the bin, as well as another system of pulleys that opens and closes the door. This allows us to lower the center of gravity of the rover as we're traversing the terrain. For the collector mechanism, we change it from a static to a variable depth collector using 2 actuators.
For the collection, we use a continuous design. First, we use a AME 214 series gear motors. The purpose of using these motors is because when the power is off, the motors do not back drive, and this is something we wanted to have in our design. Secondly, we use 2 6-inch stroke actuators. They have a 2-inch per second speed. The chain that we used was ANSI number 40 hollow pin chain, and these allow us to connect the buckets together. The buckets themselves are 12 by 3 by 2, and they're made of ACM. This material is composite of aluminum and plastic, and they're sandwiched together. This material is easy to fold, and each bucket has a capacity of 0.75 kilograms, and we estimated a dump refill time of 30 seconds. For the dumper itself, we use 2 AME 210 series gear motors. It has UHMV pulleys and 16-inch aircraft cable. We use the sheath cable because it reduces the coefficient of friction. Additionally, we use elastic tubing to keep the dumper taut as we pushed it up and down. And lastly, we use ball bearing tracks so the dumper could go up and down.
For the depositing of the regolith, we have the trapdoor on the collection bin. That is powered by one AME 214 series gear motor. It's ACM construction as well. It's mounted to an ACM cross brace that's at the top. We have a 3D printed pulley. The reason that it was 3D printed is we could mirror the flat spots that are in the shaft of the motor from the manufacturer, and we could just press fit the pulley on without additional hardware being required. We PVC line the interior. That is to make sure that none of the regolith will seep out onto our robot itself during the collection phase, and also to ensure that when the door opens, it is guided into the actual collection bin itself. It has roughly a 25 kilogram carrying capacity, and it is a gravity-assisted deposit. So when the door opens, it is gravity that's doing the work to pull it out. This is the final design showing all the components working together. As you can see, it's driving forward and backward right now. From there, we would operate the collector and plunge down. However, since we're on a hard surface, we didn't want to damage anything. So we're going to raise the collector back up, and the collector is going to run for roughly 5 seconds here. While that's operating, the robot would be driving forward at a very slow pace, filling the dumper bin. When that's full, it goes into the final deposit position, and then once there, the trapdoor opens up, and we deposit the regolith. From there, it would close up and reset, and we'd be able to go on another collection run.
For the control system, we had two systems in place. First, the manual control, which was handled by the mechanical group, and second, the fully autonomous control, which was handled by the electrical computer team. For the manual control, we implemented Telnet, which is a Microsoft program available on every Windows PC and also Android phones. We use a router to communicate via wireless internet, and the Arduino itself had an Ethernet shield and is attached to the router. And we use regular WASD controls to run the robot. For the autonomous portion, the electrical team used the CME-CAM 4 for tracking. In one of our previous classes, robot design, myself and Matt created a test platform which we converted so the electrical team can use it and test their program with. Additionally, there are IR sensors for IR crater detection and also around for collision avoidance. We plan to use time relays for the control mechanism and a micro switch for the dumper.
The electrical components that were used on the robot first consist of the motor controllers for the drivetrain. The whole purpose of using motor controllers is so you have a variable speed control so we can do small, precise movements for when we're actually collecting and depositing the regolith, as well as switching into a faster gear, essentially, to traverse the field in a good amount of time. Originally, we had two RoboClaw 2x60 amp motor controllers. Those are 60 amps continuous draw with 120 amps max burst capability. However, the motors that we have 133 amps max draw for stall torque. So we ran into an issue where we actually burnt out a set of motor controllers. After doing some additional research, we found a comparable but more robust motor controller in the Victor 888. We needed 4 of those. Those operate again at 60 amps continuous, but 150 amps max draw, so they are able to handle our motors. For the rest of the collection motors, we used a relay system consisting of larger 12-volt relays to physically drive the motors, as well as smaller 5-volt relays, which drive the 12-volt relays, as the Arduino is incapable of doing that. So from there, the Arduino is capable of controlling all of the motors with a single pin out. For the actual power of the robot, we have 2 8-amp-hour lithium polymer batteries. Those are 16C continuous draw, 25C burst draw. And for the safety of the battery itself, we have a 150 amp main breaker. For those of you that don't know, lithium polymer batteries are very temperamental and tend to blow up if you do something they don't like. Also, for the safety of the motor controllers, we have 40 amp auto resetting motor controller fuses, so we don't run into an issue where we blow out another motor controller. Finally, all of the wiring on the sensors is military specification. The purpose of this is to provide shielding from the electromagnetic field supplied by the motors when they're operating, so we don't have any fouling of the signals. This is the final design operating in sand. Sand is the closest, most common thing to regolith. It is still roughly 3 times the density, So we're not able to run the collection mechanism exactly the same as we would in the actual field of play. It is a much slower plunge, so the video is sped up here so we don't waste too much time. Eventually, when it does pick up enough for testing purposes here, it is going to stop and travel up to the top so we can deposit it. It is in steps, as the timer code was a little on the fritz at the moment when we were filming. Here, again, the dumper bin opens up. You can see the sand flow out as it would into the collector bin. Not all of it comes out as the door wasn't fully open for the test. Again, that is a timer problem, but we close and reset to continue on our next collection run.
As far as the global components of our project, for the global awareness, before starting, we did a case study on other designs from previous years and from other places. At the competition, we'll be interacting with teams from all over the world to see how they approach the same problem with different resources. For the global perspective, lunar regolith contains helium-3, which can be used for energy production, and this can set the groundwork for lunar colonization. For the awareness, actually, while we were doing progressing throughout our project, a group of students actually came, local schools came for an engineering expo, and we shared with them what we were doing with our project. Right now, actually, we're trying to communicate with them to see when we can go back to their schools and show them the finished product. Our team, as we mentioned earlier, was made of 3 mechanical, 3 electrical, and 2 computer engineers. This is the timeline for our project. It starts in September and ends in May, which is when the competition will be held. What you see in orange was what we have done, and then the green is what we started to do before the competition. This is our budget. We had originally estimated around $5,000. We ended up, through a lot of help, getting some donations with materials and machining that added up to roughly about $1,000. And we made $800 from fundraising that's not on here. And the final cost with everything ended up being $6,200.
We'd like to thank our advisor, Melissa, for all the advice she's giving us. Professor Ziccarelli, he did a lot of machining work for us, and still needs to do some as well. Penny Partanen for machining and material donation. Professor Benjamin Basil for 3D printer and gear design assistance. And Henry Ramos, he did all the welding on this. And the previous lunar robotics team that went to competition, the Pantera team, they lent us their batteries, and they also gave us some general advice of their experience. These are our references. Any questions?
Melissa, can you stand up and be recognized as the advisor? Stand up. All right, any questions?
Maybe I'll start. If it's okay. So it looks like a lot of your housing and wiring is still exposed. You guys have a plan for encasing all of that, especially I know previous groups in the past have had big problems with the spray of the regolith.
Absolutely. It's going to be a fully sealed unit. The electrical team is still working on aspects for their presentation, so that's why it kind of looks like spaghetti right now.
And when is the competition, and what can you give us a little bit of details about that?
The competition is May 19th, and pretty much 50 teams go together and compete. And we have 2 trials. They're 10 minutes long each for the trials. We also have to have a systems paper for NASA, and we also have to have an outreach paper as well. And that's why we did the engineering expo. So that's one of the first requirements. The second requirement that we need is we needed to have a kill switch on this rover, and without this, we cannot get past the safety inspection of the competition for safety reasons. Second, we also have to show the panel that we could communicate wirelessly and that we could stay in our bandwidth that we get. There's 11 channels, and we're going to be on channel 1, and then the next team is going to be on channel 11. So those are one of the things that the competition requires. Additionally, we have a dust tolerant design, so we have all of our gearboxes right now are covered, and we 3D printed them using your printer, and we have an acrylic on the top covering that.
I think you guys did a great job. I mean, this is certainly a significant project. I think the amount of work that went into it is pretty substantial. It should be fun. And one more comment, just Matthew, every time you present, I feel like I should like fall asleep. You're so comforting. Anyway, it's fine. I know you're a natural or something.
And that's an accolade. All right, I got two. Where are the other team members in a big project like this? You said it was multidisciplinary.
Yes.
Where are the other disciplines?
Due to the time shift of the presentations, the electrical was here, but he left because of the.
Oh, because of our lateness?
He has
Yes.
a final.
Yeah.
You're at fault.
All right. Okay, and then for the buckets, I notice you're using rivets. Will that be able to deal with the dynamic loading, picking up all the regolith and all the other activities going on with those buckets?
The regolith itself is extremely light compared to sand itself. It's very similar to cake flour, actually. We didn't test it in cake flour because we didn't want to buy that much cake flour. But the actual rivets themselves, we did some testing on it originally. The biggest problem that we had initially was the grip length on our rivets were not of proper size. So it did not mushroom properly on the other end, and we had our first bucket that we tested kind of pop out. We did some research, found out that, oh, the grip length wasn't long enough, and that remedied the problem. No.
So have you tested it with the longer rivets?
Yeah, that's what's in there now. That's what we were collecting the sand with there.
Okay. All right, those are my questions.
The only question I have is on the autonomous piece. Is this thing going to run by itself, or are you going to be radio controlled?
It's supposed to run autonomously. The manual control is there in case autonomous does not
Doesn't
work.
work.
Since we only get 2 runs, we can't afford to go in there and have the autonomous fail and just say, oh, we'll do it manual next time. We have to be able to take over and still attempt the competition if plan 1 fails.
Okay, and how does the autonomous nature work system?
The autonomous works back here. There's a camera. And this
Okay.
camera, there's going to be a light source somewhere. So we were using a phone, which emits a light. And that camera follows wherever the beacon is, that's where the dumping area is going to be at. So it'll find that area, it'll go to it, and then that starts off as the 0 point. After that, it'll travel across the field, and it has iris sensors to detect the walls, and once it detects the walls, it will know when to stop, and then in that area, it will start digging. On its way back, it needs to turn. They plan to do a wall follower, so it's going to follow along the wall and then come back. The robot then needs to turn back around, and this camera is going to redetect the beacon, and it's going to go to it again, and then the dumper here is going to come up, dump the soil, the BP regulator, and then after that, it'll keep doing that until our time limit is up. That's how that works.
That's amazing. The key is, it's going to find that light?
Yes, that's the hard.
question.
That's
It's going to
the.
find that light?
That's the,
We tested it out in the room, and it was pretty reliable. We had a phone screen.
What if it gets a little off kilter, you know? 2 degrees.
The camera itself is pan and tilt, but we tested it out with the test platform that you mentioned before. We had a little omnidirectional robot that we put the camera on, and he was moving the cell phone around it in a circle, forward, back, up, down, and it was able to follow the camera around pretty reliably.
Thank you.
Dr. Delakravich.
Good work, good engineering work. I give you high grades. But I have a couple basic questions. This is a mining robot for application on the moon.
Correct.
There are 2 specifics about moon: low gravity and low temperature as well.
Right.
Well, third one, no atmosphere. So first question is, you've chosen to use a Caterpillar drive system instead of using the concept of a moon buggy, basically the little jeep that was used by astronauts years back. This is fine if the surface is nice, flat, and everybody's happy. Moon surface is not really always nice. So the question is, I fell down, I cannot get up. I mean, yes, you mentioned you're trying to put the center of gravity as low as possible. Good. But still, how do you justify using this concept, Caterpillar, versus using flexible wheels that can negotiate large variations in a terrain?
Well, for one thing, we have size limitations.
Excuse me, you have to speak up, I cannot hear you.
Well, one of the things is for the competition, there's actually size limitations for the rover, so we can't do anything extremely large. But other than that, this is strictly for the competition. If we were to go to the moon, we'd have to consider more aspects to it.
On top of that, also, we did some case study research through the military, actually, where they noted that while wheels are more reliable because they provide redundancy, they also don't supply nearly enough traction because treads disperse the weight more evenly across the terrain. So it provides flotation. So you're not really digging into the sand so much as you're riding along the top of it. So that's going to help us in the fact of traversing bumpy, lumpy soil.
Well, the gravity on the moon is only 1/6 on the Earth.
Right.
So you're not going to be sinking that much of the soil.
Right.
I think you should reconsider the drive system conceptually and ask yourself, why did NASA decide to go with wheels rather than Caterpillar?
Actually, they're also planning to use a track system on one of their prototypes for the moon. Also, the last winning team was Iowa,
Right.
from the NASA Lunar Robotics Project, and they also use a track system similar to ours. Theirs was different because they custom made, they had chain-driven tracks instead, and they had bended aluminum cups holding to drive it. So we got the idea from them, to do this implementation.
Did NASA, just to add to Dr. Delakravich's question and to help you guys out, did NASA give you any prescriptive guidelines for the traction? Did they?
No air in your tires because of the
Yeah,
atmosphere.
no pneumatic tires.
That's right, purely metallic. Another question, hopefully much shorter. There are tremendous variations on temperature on the moon. Is any of the components in your entire design sensitive to such huge variations in temperature?
Our design was not, we weren't required to make a robot that's Mars worthy, as we call it, lunar worthy. So, no, that would be, our components would never survive that atmosphere.
It's a lunar simulation
Yeah.
on Earth. It was never intended to physically go to the moon. So.
Thank you very much. Perfectly okay.
That answers all the questions. All right, are there any other questions or comment? Excellent work. Thank you.